driving giant 7-segment LEDs today on Mikey's Lab. Hi, and welcome back to the lab. If you haven't already, go ahead and click that subscribe button down below to ensure that you get all the updates from the lab. Today we are looking at driving some rather large 7-segment displays. You can see the completed circuit that we're going to be working towards down here right now. If I grab my digital calipers, as most of you probably know, 7-segment displays are consistently made up of 7 LEDs, right? And each segment is controlled individually to display a number. Now, usually these displays are about 1 inch tall, right? These ones are, pick the display up itself. As you can see, 12.2 centimeters, or approximately 4 inches. So these particular 7-segment LEDs, unlike their smaller ones, have a significantly higher forward voltage, which makes them a little more difficult to deal with. And that is the focus of today's video. Right, is how we're going to go ahead and how we are driving these. Now, there's a secondary motive to this for me too. As you can see by the fact that this project here is completed on this breadboard, I have figured out how to do it, and it's part of another bigger project which will show up in a few months. But I did this on a small breadboard, and now I'm out of room. And I'm not quite done how far I want to go. So what we're going to do today is we're going to dive down to the bench, and we're going to replicate this circuit on a bigger breadboard. I'm going to take you with me, and I'm going to explain the decisions I made, why I made them, and why I think that that's the way that this needs to be. So first off, dealing with these, again, as I said, they have a higher forward voltage, around 11.5 volts for decent lighting. The data sheet says that their forward voltage is 12 volts. I don't believe the data sheet. These come from China. A lot of times it's a little iffy. They seem really bright at 12 volts. So we've included a dimmer circuit in here using a MOSFET, which I will explain in a little bit, so that we can extend the life and power these a little lower than the 12 volts that they talk about. However, my lab bench power supply, this is the first project using the new power supply. And if I can get this into shot here. Right, I don't know if you can see this or not, but it's currently set to 11.99 volts. Right. This says it's drawing 200 milliamp. Part of that is because it's connected to the FTDI cable. The FTDI cable gets powered from the circuit or the PC, but if I withdraw that, it goes down to about 100 milliamp for both of these running, depending on how many segments are lit, obviously. Okay, so when working with something this big that has this level of current draw, we had a couple of options. Right, we'll flip over to the microscope here for a second. I could have gone with a normal custom LED driver, like the TLC 5040 that you see here. I probably would still have had to use transistors. I haven't looked at the data sheet to see if this can handle 12 volt forward voltage. This is custom designed and purpose designed to drive LED displays, but I decided not to go that way. All right, we could have gone with our friend that we saw with the last project, which is the TPIC 6B595N. This is a high voltage shift register. Dealing with a 12 volt forward voltage is kind of like killing an ant with a bazooka with this thing. This is what we use to drive the Nixies to handle the 170 volts that it needs. So these are not the cheapest thing, and I don't have a whole lot of them in the lab, but it could have been a solution too. Instead, I decided to go with a dual chip solution. The first stage of the solution is this guy right here, which is an 74HC595 shift register. Yes, I know this is not 12 volts compatible at all, but we'll get there in a second. So this will handle the controlling of the digits based off of 4 Arduino pins, I believe is what it came out to at the end. Right, and the output of that will be fed into a ULN 2803 Darlington transistor array. This will allow us to sync the 12 volts, and this display is common anode, so we source 12 volts and we sync whatever we want to turn on. That will allow us to sync that 12 volt current through without an issue. Won't even get hot, since this is designed to pass a lot more amperage than what this is going to be passing. And then on top of that, we are going to use an IRF 540N transistor to allow us to do the dimming. This will allow us to programmatically dim the LEDs. If you can see, if we go back to the bench here, you can see that when the numbers come on, I'm actually using programmatically a fade in for the number. Just so that everybody knows, that flash that you're seeing right now is intended. It is done programmatically. Okay, so we've seen this working. We know that it's drawing 12 volts. We've talked about the parts that we are going to use to do this. So let's recreate the circuit on the new breadboard. Alright, so here we have the bigger breadboard. Again, this was just a narrow-sighted mistake on my side, but at least it lets me take you through the process. I wanted to take a better look at these 7-segment LED displays that are big. Ignore the shiny and the dots. There's a protective coating over top of them that I haven't peeled off yet. I will once they're in the actual product. If we look at the back, there are 5 pins across the top, 5 pins across the bottom. There is a common anode for both the top and the bottom. In this case, it is black and orange. So, pin 3 at the top and pin 5 at the bottom. Alright, so pin 1 at the bottom. So pin 1 starts over here, goes across, and goes across. You can see that there are numerous LED modules in here, and each of them correspond to the individual segments. This is almost everybody, I think, will have seen one of these. Maybe some of the younger kids are of the age where everything is by LCD and nothing looks like this anymore. But these were used all over the place. The bigger the bigger size will make sense with the rest of the project. But let's go ahead and create the driver circuit for this. We're going to ignore this board in this particular video. After this circuit is done, I want to add the code to this circuit to make it an I2C slave and allow it to be controlled by other things. This is part of a bigger project. The video on creating an I2C slave device will probably be the next one to follow after this. So I'm going to temporarily set aside the 7-segment displays. And the next thing I'm going to do is I'm going to grab the Arduino from the original breadboard. And we're just going to put it on this side over here. This is one of my battle-hardened Arduinos. You can tell because there's a fair bit of stuff on it. I think this was one of the early ones from one of my first rounds of purchases of Arduinos. Okay, so the other thing you may notice with the setup of this breadboard is I have the 12 volts from the power supply going to this rail, but this rail connected to nothing else. So, one of the first things we want to do, because I like single voltage source things, is we want to take 7805 voltage regulator and create a 5-volt rail for the rest of the circuits. So, I'm going to go ahead and grab the 7805 voltage regulator. I'm going to put it over here. Actually, I'm going to put it in the middle. Okay. Alright, so for the power wiring, one of the other things I don't like is all the loopy mess that came out of the other one. So I'm going to grab a breadboard kit. So we're going to put the 12 volts on the in pin. We're going to grab this gray guy here. I'm going to use him to bring ground to the ground pin. And then we're going to take this slightly longer one here, and we're going to bring 5 volts to the other rails. Okay. So that should provide us the 5 volts. For those who have been watching the channel for a while, you know that trust then verify is kind of one of my mottos. So let's grab the multimeter, set it to volts DC, Verify we have 12 volts coming into the board. We do. Verify we have 5 volts here. We have 4.98. Let me bring that back down so that you can see that. As you can see, we have 4.98 volts. And we have 12 volts. Everything is kosher. So let's turn the power supply back off. And we can put the multimeter away for a second. So the next piece of wiring that we need to do is we need to power the Arduino. So let's take a look, couple of these little jumpers here. Alright, we can see that we have a VCC here. So we'll use a yellow jumper for VCC. And we'll use a black jumper for ground. Okay, so now if we turn the power supply on, we should see the Arduino light up. And the Arduino lights up. Perfect. The power supply back off. Alright, so the next thing that we want to do is start to bring over some of the ICs. First set of ICs that we're going to install into the breadboard is going to be the 595 shift registers. The final product for this project will actually have 4 digits, but we're going to maintain the 2-digit display at this point. The outputs of the shift register are on this side, so yes, pin 1 towards the Arduino. So the outputs of this particular chip are primarily on this side. So we're going to point them this way, since we're going to do the Darlington Darlington transistor arrays over here, and then those are going to go out to the display. So if we can keep things in pattern, that'd just be perfect. So we're going to go ahead and we're going to stack those two together. Okay, so now we're just going to switch over to the PC for a second. We're going to take a look at the data sheet for the 595 shift register. Alright, so here we have the data sheet. Scroll down till we see the pinout. Okay, there's the pinout. So pin 16 is VCC and pin 8 is ground. So pin 16 is VCC, pin 8 is ground. Pin 16, VCC. Okay, and I'll just turn on the power supply, make sure we don't get any magical smoke. No magical smoke. Okay, so we have power and ground hooked up to the shift registers. Now we're going to take a look at some of the control pins that the shift register uses. If you look at the playground sketch in the tutorials that Arduino has for using the 74HC595, you'll find that master reset and output enable are usually just tied out to ground and VCC respectively. I'm going to actually take control of output enable because it will help us with making the display a little more perfect and being able to turn it off at times. But master reset is active low, so we want to take that master reset pin and we want to drop it or pull it high. So that's going to be the next step that I do. Drive it high. Learn to count, Mike. Pin 10 high. Okay, so the next connections that I want to do, we're going to take a look at the source code just to see the pins that I've chosen. So the data pin is pin 14 of the shift register, which will go to pin 11 of the Arduino. Try to find as close to the size as I need. 11 to pin 14. Then pin 12 to pin 11. So we're going to take a longer white one here. Pin 12 of the shift register goes to pin 8 of the Arduino. Alright. So as you can see, these little breadboard wires are going to make this whole thing a lot neater to work with. Okay. So the next part we need to do is we need to connect this, we need to connect the signals from the first shift register into the second shift register. At this point, everything of course but data. Data comes out from the existing shift register. Alright, so data is, go back to the data sheet just to make sure I don't screw anything up. Data is pin 14. 16, 14, there it is right there. Let's see, do I have one that's approximately the right size just to jump those two? One more bit. Not entirely, so we're going to grab this guy right here. Okay, data out on 74HC595 is pin 9. Data in is pin 14. So we bridge those two like this, and that will allow data to flow from this shift register to this shift register. Okay, now we need to replicate the clock signals. All right, I'm actually going to start using some of the actual jumper wires now, because this will start to get a little bit crazy after a bit here. So pin 12, right there, to right there, there, right there. And then here to right here. That should have our shift registers up and running. So now we're going to go ahead and we're going to test this theory with a couple of LEDs. Wait. We're actually just going to pop it into that one there. And let's turn some power on and see what happens. And as you can see, it shifts through the data, so we know that the shift registers are working. Perfect. Let's pop these guys out of here. Now let's add our ULNs, our Darlington arrays, which I'm going to place pretty much right across the way from the shift registers. These are passive components, so they don't need power and ground necessarily. They drive it from from the circuit that feeds into it. The other thing we're going to do is we're going to set up our transistor at this point. Okay? So I'm going to go ahead and plug the transistor in here. Right, according to my software, I believe I set pin 6 for brightness. I did. Actually, I'm just gonna pin 6. You just once again verify where the gate is. So we make sure that the gate is attached to there, and the drain needs to go to ground. So we're going to grab a little piece of jumper here and attach the drain to ground, like so. And then I'm going to go ahead and connect our two Darlington arrays into the MOSFET, which is controlled by pin 6 on the Arduino, which will allow us to dim the circuit. Okay, so there's 2 steps left to do. The first step is to connect the outputs of the shift registers into the inputs of the Darlington transistor arrays, and then we can test the whole thing. So I have a couple of 8 wire pieces done here. On the shift register, pin 1 is on the other side of the chip, and then the rest are in order on this side. Alright, so we're going to do the same thing with the next set. Okay, so we're just going to power up and we're going to see if we have any magical smoke this time. No magical smoke. That was a good sign. Alright, so we need a small resistor. This one really has no resistance to it whatsoever. Alright, but I'm going to go ahead and just place it in the way here. I think this is like 2 ohms, if that. And we're just going to place that in line with the power lines for this this 7-segment LED display, and we're going to connect pin 1. Alright, so as we can see, we now have the circuit recreated on a breadboard, which has a lot more free space on it for me to work with. It is counting perfectly. So why don't we just take a couple of seconds, we'll drop to my PC, we'll review the code, and I'll show you how the software side of this magic works. Alright, so right off the bat, as anybody who has watched this channel for a while knows, I'm not a hardware engineer, but I am a software engineer. So there are some changes to what you would see by default with this project. So, alright, so the first thing you notice with my code is a lot of people, including the Arduino playground, tend to use integers to define pins. I don't understand why. Why you would use a variable to define something that never changes is beyond me, since it's going to take up program memory, and the Arduino has a very finite amount of it. So instead, I tend to use defines. So that's what we start off with. We define the pins. This means what a define is when the compiler goes to compile this, it statically links this value in. So it doesn't take program memory or memory at all. Once this for this to work, it just substitutes the text in as it's compiling. Alright, so the next thing we have is an array that contains the bit values or byte values for each digit. Now it is in order, so at the very left over here is 0, then this is how to display a 1, this is how to display a 2, 3, etc. This makes it easy to shift these values out and have them display properly on the 7 segments. I also have a decimal value here which turns on the decimal points. Now the way that this can work is you AND them together, right? And the decimal will light up with that digit as well. Because we have 2 digits, there's a two-value array for digits, which holds what the current numeric value in each of the digits is. Now we have a few registers that will be used mainly when we do the I2C side of things. So the display brightness, the blink delay, that's the flash in between where the screen actually, or the 7-segment LEDs actually turn off before changing values. And then the current number that will be displayed. This is not used in this particular this particular source code. So in our setup, we set up all the pins that we want to use to output, and we turn off the display. Turning off the display right away means that we don't get the as bad random values when the circuit first powers up. So in the loop, we simply loop from 0 to 100, counting. Right. First thing we do is we parse the number, the value of I, into digits. This is done with a magical formula down here. First thing we need to know is how many digits we have, so we use a string.length. That will tell us how many digits there are. From there, we go through each of the values by iterating an order of magnitude, right, and then using modulus on that to determine what the remainder would be, which will give us the number that we need to display. This is a little more compact version than, let's say, Great Scott's. He did a video on using these things before, and he kind of went the long way on this part, but he's definitely a hardware guy. I'm definitely a software guy. So after we've parsed the digits, what has happened now is that saved the digits to this array up here that we talked about earlier. Right, from there, we update the display, which over here we turn the display off if it's already on. We blink the delay, which is that flash thing there. Right, so whatever value we have set in blink delay up here is how long we allow the display to remain turned off. Right, then we digital write the latch pin low, which means we're now going to send more data into the shift register. Then we use the shift out command with the data pin, the clock pin. I personally always like to use the most significant bit first. Now what that means is the further left you've gone on the number closer to the 0B, the more significant the digit, because the more impact it has on the value of the digit. So we're shifting out the first one there first. And then we just look into the numbers array and find the byte value for the digit we want to display inside of there. Then we write the latch pin high, which tells the shift register to change all of its outputs to the new value that we said. We turn on the display and we do a fade in. Now fade in, if you go over here, fade in simply scrolls through 0 to display brightness, right? Writing to the analog pin, pin 6 to change the value of the MOSFET seeing and do the actual fade. For those that are interested, turn on is just a simple digital output right low to the output enable pins on both the shift registers. Well, there you have it. Controlling giant 7-segment LEDs with a much larger forward voltage than your standard LED using Jelly Bean components and an Arduino. We're set up for the next part of this project, which is to add the I2C slave control to this. So I hope you learned something today. Thank you for joining me in the lab. Go ahead and smash that subscribe button and that like button if you enjoyed this, and I will see you next time.